Hello, fellow citizens. Welcome to my Chalk Talk. Today we're going to talk about how a do-it-yourselfer can release all the energy from inside a superconducting magnet if they happen to have one and they wanted to do so. In our superconducting magnet, we have 89 amps of current that is flowing in a coil that has an inductive property of 70 henries. The idea of a henry is that if you apply 1 volt or connect a 1 volt battery to your coil of wire, the amperage will start from 0 and it will climb at a rate of 1 ampere per second current rise. So in our case, for 7 henries, it would need 70 volts to make a 1 ampere current rise per second. Or flipping it around, if I still had that 1 volt battery, I would have a 1/70th of an amp per second increase, 1/70th of an amp per second, growing as the current would slowly grow. To give you an idea of the size of a 70 Henry coil, shown here in this coil of wire, it's about 300 pounds or more, so it's a pretty big coil of wire. It also is made of superconducting wire, which means that if you put this into a bath of liquid helium and everything gets cold enough down to the temperature of about 4 degrees Kelvin, it will have a very interesting property called superconductivity, where it loses all of its resistance. So if there was some way I could get some current flowing in that coil, it will remain flowing for years to come. There may be some minor loss each year, but that's a topic for another story. Well, the secret to getting energy in and out of this coil of superconducting wire is to have a little section where it is next to a little heater. Well, what happens if you heat up a little section of superconducting wire? Well, at some point it will get to a temperature where this property of superconducting disappears and you're left with a plain old piece of wire that contains a little bit of resistance. Well, in this particular setup, and whatever length of wire they used and whatever property of the superconducting material, it gets a resistance of 7 ohms when it loses its superconductivity. Well, 7 ohms means that you need 7 volts to push 1 amp through that piece of wire. Well, let's say that we happen to flick this heater on, and by the way, this heater, it really doesn't take much heat. It is powered, you can power it by a little transistor 9 volt battery, one of those small boxy little things the size of your thumb, end of your thumb or so. That's enough heat to make this rise to become non-superconducting. Well, let's just see what happens if we did have 89 amps flowing in there. We turned on our heater. Well, that would suddenly get 7 ohms property to it. Well, the way these things work is 89 amps times 7 volts per amp. We would see 623 volts across that 7 ohm resistor. To calculate the watts, which is the amps flowing times the push or the voltage on it, 89 amps times 623 volts would give us 55,447 watts blasting out of there, and that's all heat. 55,000 watt heater, which would be equivalent to about 50 or so home plug in the wall, warm your legs heaters all at once. Well, there's another aspect here about what would happen to the current in that coil if you now have a pressure of 623 volts on it. Well, what you do is you take 1 amp per second divided by 70 volts, that's the Henry, the inverted unit for Henry. So 623 divided by 70 would mean would drop at the rate of 8.9 amps per second. So after about 1 second, we would have dropped from 89 amps down to about 80 amps. This involves calculus, but if we take it in 1 second intervals, let's see what happens in the next second. 80 amps times 7 volts times 7 ohms, 7 volts per amp. We still have a voltage drop across that section of non-superconducting wire of 560 volts. And we do the calculation again. 80 times 560, we get about 44,800 watts in the second blasting out of that zone. Now, since our voltage has dropped a wee bit, 560 divided by 70, we're now slowing to 8 amps per second to take our next increment. Well, 80 minus 8, we get 72 amps still flowing in that coil, times 7 volts per amp. We have 504 volts across that resistor, which works out to 36,000 watts, and a little reduced. Now it's dropping a little bit less. We're going to drop down about 7 amps per second. So 72 take away 7. On the next step, 65 amps still flowing in that coil. So we get 450 volts, 30,000 watts, and a little bit slower rate of 6 amps per second. Do it another time. We get about 410 volts, and that would be about which second? First, second, third, fourth. After 5 seconds, we still have 410 volts blasting at 24,000 watts with approximately the same 6 amps per second for the next second. So we would be taking 59 amps, take away 6 would bring us down to 53. So it goes. To get a more accurate picture, I'd have to remember my calculus. So what we see there is if a section of this superconducting coil were to lose its superconductivity, we see a massive release of energy. 55,000 watts would be like 5 arc welders, about 10 arc welders going all at once. Now all that energy would then be caused to boil off the helium. So if you want to see what that looks like, type in superconductor quench or MRI quench, and you'll see some nice video action shots of superconducting magnets blowing their stack like an inverted rocket. Well, to prevent that from happening, they add in a safety circuit of a diode or 2 or 3, so that if that section did become 7 ohms, well, diodes have a property where that no matter how much current flowing through them, they maintain roughly the same voltage drop of somewhere around 0.6 or maybe even 1 volt if you have a whole lot of current flowing through them. If you had a Schottky diode, which is really great for handling high currents, maybe 0.8 volts per diode at that kind of amperage, as long as they're high amperage diodes. Alright, let's see what happens if we did have 2 volts drop across those two places and we're plowing 89 amps through it. Well, amps times volts, 178 watts would be plowing in that area and warming up the liquid helium, which is a whole lot less than 55,000 watts. So flick that switch. If you did not have anything external hooked up, you're not in too much danger. So they definitely have protective diodes built into your superconducting system. Alright, here's my primitive grade school drawing of a superconducting coil in a bath of liquid helium with our 7 ohm section that has already been heated up to become non-superconductivity with our protective diodes. But now we're going to have shown a probe. These may be 2 or 3 feet long dipping in from the outside world to touch and connect to our circuit. Now for this discussion, for this do-it-yourself discussion, I'm showing two diodes hooked one way and then the other, because diodes not only have this property of a 0.7 volt drop across them, they also conduct electricity or current basically in one direction. Only if the current tries to go in the other direction it's stopped, like a one-way door. And you can see how the symbol looks like an arrow pointing one way with a bar on the other side. Just for your information, the electron current, that's the actual particles usually moving in a wire, is allowed to flow through this symbol from top to bottom, even though it may be kind of illogical. I won't get into that argument. It has something to do with Benjamin Franklin choosing current to be the other direction, but okay. So in the second diode, the electron current could go in the other direction. So putting these two cross diodes like this, I think they're called cross diodes, it does not matter which way the current is going to be coming out of your superconducting coil. Either way is going to be accommodated to give it a very gentle 0.8 volt drop, or somewhere around 1 volt, to gently burn off your energy from that coil of wire. So you want to mount this on a heat sink with a little fan to keep it cool, but it only will need to be stressed out to release, let's say at the very beginning, 90 amps times 1 volt, 90 watts of power, which is your typical. It's not that much. And if you release that over 2 hours, there's no dramatic explosive situation going on. Alright, just for your fair warning, I'm not an expert, and you have to be an expert if you're going to actually try something like this. So it's just for informational purposes only, and do it at your own risk. I can't afford to pay for your blown up magnet. Alright, that's all for now. Thank you for listening.